Welcome everybody to From Quantum Reality to Spiritual Possibility, Ideas from Science and Theology. I'm Dr. John Fairless, pastor of the First Baptist Church of Gainesville, Florida, and it's my privilege to put together this brief video series discussing some of the advancements in science and quantum reality, as well as the ways those might apply in our spiritual lives. This is a study I've prepared for our Wednesday night Bible study group. Whoever you are and wherever you're tuning in from, I'm glad you're here. One of the goals of our study has been to help us embrace new understandings and especially to be able to have a conversation with friends, neighbors, family, whomever it might be, about our faith, especially in light of some of the ideas that go around in our modern times. Now that's kind of a funny word. I'm actually going to talk about being modern in just a moment. But I'm going to begin with a couple of quotes that have been meaningful to me for a number of years now. These are from a couple of professors during my time at Vanderbilt Divinity School in Nashville, Tennessee. Professor Peter Hodgson had a great quote that has stuck with me ever since I first heard it in class in 1990. How is it possible to speak meaningfully of God's presence and action in the world today? You know, it's always the presence of God, the action of God in our world that leads us into faith. And we want to be able to speak about that. And we want to be able to talk to people with meaning. And yet in our time, it seems like people, though they're very interested in spiritual things, haven't been that interested in the traditional ways the church has talked about our faith. So I have taken Professor Hodgson's challenge over the last few years to be, well, then how do we find ways that we can engage people in meaningful conversation? Professor Sally McFaig also said this: the primary thing that our time lacks, and hence a task that theology and the church must address, is an imaginative construal of the God-world relationship that is credible to us. Now, that's a mouthful, I know, but it's that phrase, imaginative construal, that really stuck with me. How do we engage our imaginations? How do we help people understand the passion that we feel, the joy that we feel, the excitement that we feel from knowing that God indeed is with us in this world and that Christ is the very picture of that? God has opened a relationship with us and in fact with everyone and everything in the entire world. How do we speak of that? And again, Professor McFaig says our time lacks this. So we want to work on it. Another famous quote, "What the world needs now is love, sweet love." Thanks to Burt Bacharach, a composer from a few years ago. I just kind of try to keep that in mind. As many of you who know me know, I can kind of get a little geeky sometimes when I'm talking about theology, and especially when you combine that with science. Now, which is, first of all, what is quantum? It's a word that has begun to go around a lot in our time, and most people know that quantum has something to do with science or it has something to do with computers, but nobody's really that sure of exactly what quantum is. Well, you're going to see why that's true, but the first thing to realize is that quantum is everywhere. It's at your bank, it's at your grocery store, it's in your pocket or your purse. All of the major banks in the world, in fact, pretty much nations, governments, everyone that deals with huge amounts of money and lots of lists, it's all digital these days. And many of the advances in computer technology that allow banks to keep up with your funds, they don't necessarily hold all of your dollars in dollar bills anymore. It's all zeros and ones. It's all on the computer. That's enabled by quantum technology. When you go to the grocery store, I can remember being a grocery clerk back in the old days when I was a teenager, and we used to have to put price stamps on everything, literally, and you'd pick up a can of beans and say, oh, 34 cents this week. And if the price changed, we had to rub the old price off and put a new price on. Well, you don't find prices on individual items anymore. Very rarely. It's all in a barcode. And you go to the front line and you check out, and they run your stuff over a scanner, which reads the barcode. That's all quantum technology. And very few of us anymore do not have a cell phone in our pocket or in our purse. And even if you have what you might consider to be an older cell phone, maybe it's 5 or 10 or more years old, even that older cell phone, and certainly some of the new ones, they run on quantum technology. So it's everywhere. It's at the doctor's office. It's at the hospital. It's everywhere. Now, we are going to answer that question. We will answer the question, what is quantum? But we will not be covering the subject in its entirety. There's just no way. People spend their entire careers studying and working in the area of quantum science, and they still haven't covered the whole subject. I guess it's kind of like the Bible when you stop and think about it. Even though we may have read it all, and even though we may have studied it, as I've been privileged to for more than 40 years, I don't claim to understand all of it. There's just no way. Well, quantum science is kind of like that. I am going to try to keep things on as simple a level as possible. I'm not an expert scientist. I'm not really an expert at anything. I'm not much of an expert at preaching or teaching the Bible, but I have read a great deal and tried to study pretty hard on this intersection between science and our faith and our theology. And the explanations can get technical in a hurry. I'm going to try to keep them simple. We are only going to touch absolutely the things that we need most. What we're doing is searching for the ways that quantum reality, which is our representation of science, intersects and strengthens the spiritual possibility in our lives, which represents our theology, our faith. Well, I want to get in mind, and I want us to think in terms of 3 general periods in time, and to divide all of time into just 3 periods is, I realize, a little bit simple. But for our purpose, it's really going to help to understand the mindset of the ancient world, the pre-modern world, and the ways that people before the advent really of language and of much education, before the advent of science, the ways that people thought about the world. Then we're going to call the modern world beginning at about the year 1500 or so. 1500 CE, that's the Common Era. That is what many of you may have grown up like me knowing as AD. It's just changed now. We talk about the Common Era, but it's still the same year, around 1500, and we begin to get advances in science, and eventually we get the Renaissance and the Enlightenment and all other sorts of things like that. And then I want to talk about our contemporary world, which is also sometimes called the postmodern world. Almost everyone agrees that the world began to change and our attitudes began to shift somewhere back during the 20th century. Some people say it could have been as early as the 1920s. Others say, no, it was more like post-World War II, the 1950s or 60s. And some identify the shift as late as the 1970s and beyond. But the way we began to think as a society, the way people began to think, has shifted, and it's not exactly the same as it was in the modern world. We live in a postmodern. There's a way to think about some of the highlights of each of those time periods. In the ancient world, the pre-modern world, everything was seen to be as a mystery. When people started thinking about the way the world worked, they didn't know why the sun came up every day. They weren't sure what made a rain cloud appear and drop rain on the earth, or why the weather turned cold and it began to snow. There are all sorts of explanations when everything is a mystery. The view of God or of religion is that God or the gods are very far away. They're unreachable. They're unknowable. The gods, or even God in our tradition, might not necessarily have that much to do with us in our everyday world. Although religion was often the leader in society and in interpreting and answering these kinds of questions. Religion has been important in pretty much every society all the way down through time. We've never discovered a society that had no concept of religion. So when everything's a mystery and the gods are far away and unreachable, unknowable, I guess you have your religion and you sort of hope for the best. Now, in the modern world, things began to shift a little bit because science and math and other disciplines, education moves forward, and there becomes the concept that everything is a machine. Everything fits together. There's cause and there's effect. We're going to talk in a moment about people like Isaac Newton, who began to put order into the world. Religiously, we have the poem from Robert Browning, God is in his heaven and all is right with the world. God was indeed sort of above our lives, but much more involved, and as long as we obeyed the commands of God and did the right things, everything would work according to a certain order. Science really begins to take the lead in the modern world. We become very used to thinking and understanding things in order. We look for proof. We want things to be demonstrated. And so for several hundred years, everything seemed to work just like that. But when we enter our contemporary world, when we become postmodern, again, things begin to shift. Now, instead of everything is either a mystery and far away, or everything is a machine, and we know that if we do this, then that will happen, we begin to realize that it doesn't always work that way, that everything is possible, but that means that everything can be chaotic sometimes. Things happen without an apparent cause. We have a couple of different views of religion. There is God with us, which is certainly comfortable to many of us in our faith. God is very much involved in the world. God is very close to us. Or people may have an attitude more like, God, who's he? I don't need God. I've got science. And in our postmodern age, religion and science do one of two things. They either compete for the hearts and minds of human beings, or they cooperate. They inform each other. And their work together leads us to a deeper understanding. You know, it's that last idea that we're working for in this course, and how religion and science can indeed help one another as we're trying to figure out what it means to live in this postmodern world. Well, our next phrase says, it all begins with light, and that's very true, whether you're talking about science or whether you're talking about religion or faith. It's interesting to me, and this is our first point of common contact between science and faith, between quantum reality and spiritual possibility. It all begins with light. And we're going to use the research and the discoveries and the scientific development of science, as well as thinking about it from a religious standpoint, to kind of work our way through the rest of this first session. In the book of Genesis, chapter 1, verse 4, we understand that the first thing that God creates when God creates the world is light. And God said, "Let there be light." And there was light. Now, it's not until the fourth day that God creates the sun and the moon and the stars. Someone in class last week said, well, what in the world was that light if we didn't have any sun? Well, you know, that's a very good question, isn't it? But even the story of creation in our faith tradition begins with light. For science, it's often described as the first moments of the Big Bang, when everything began billions and billions of years ago, and all of matter, everything that's ever going to exist, began as a tiny, tiny little point of extremely compact matter. A singularity, it was called. And then, kaboom! It exploded with energy, which was expressed as heat and light. The beginning of the world, according to science, according to the Big Bang, also begins with light. Now, isn't that interesting? And so that's the first thing we're going to see that science and religion have in common. We're going to encounter several others along the way. But let's continue to think, as scientists did, particularly in the modern time, just what is light anyway? How does it come to us? And how does it accomplish all the many things that light accomplishes? We want to talk about Sir Isaac Newton as kind of a representative of the scientific age, And Isaac Newton was generally acknowledged as being the leading scientist of the modern age. It was Newton who had ideas about things like gravity. Most of us think of Isaac Newton sitting under the apple tree, right? Apple falls down. He's like, what makes that fall? But he was very much involved in mathematics, very much involved in science, and helping to understand the way the world operates. We all learned Newton's laws when we were in school. Newton's laws of thermodynamics, Newton's laws of motion, all sorts of things. Newton was very much responsible and very symbolic of this idea that if we can just figure out all of the laws of nature, then we will know how the world works, and that everything has a cause and an effect. For every action, there is an equal and opposite reaction, right? And Newton was very gifted, and his view of the world really did open up lots of new understandings. And for hundreds of years, there wasn't a lot of reason to question Newton's laws and the way our physical world worked. Now, Newton was also very interested in light. And he was pretty sure that light was made up of a beam of particles. He called them corpuscles in his day, which is just another word for a very small bit, or a little piece of light, a little particle of light. And as Newton began corpuscles of light worked, it explained a lot. It helped the scientists of the time understand how light came from the sun and got here to our Earth without having anything in space for it to travel through. They were trying to figure that out because they couldn't conceive of something that could travel long spaces through nothing. And there was another theory of the day that said, well, space must be filled with an invisible substance called the ether, and that's how the light beams, these light waves, can travel. They knew that sound had to be carried by air, and waves in the ocean have to be carried by the water. When Newton said, well, no, wait a minute, light is a series of beams, these little small corpuscles, well, it just made sense. It also helped to understand the way light was bent and refracted, for example, in a prism. And they could observe that light would be broken up into different patterns and that it would arrive in, sure enough, little packets, little particles, these corpuscles that Newton theorized. So, again, so far, so good. They're figuring out how light works. But then along came a man named Thomas Young in the late 1700s, early 1800s. And Mr. Young liked to do experiments, and he too was working with light, monochromatic light, which means light of just one color. So that, it doesn't break up into other particles. It's just made up of the one stream. It doesn't have to be diffracted. And as he was playing around in his laboratory, he was sending light through a slit in a solid object. And as you see on the illustration there, the light beams would come, and if they hit the solid object, they would be deflected, they would bounce off, and if they passed through the slit, they would move right on through and go to some type of board or some type of substance that would record those light beams hitting. And you could see with just one slit how the whatever shape the slit was, the light beams would arrive through the slit and travel to the photosensitive material, and it would look just like the slit. But then one day he did something different. He decided to put two slits into that object, and that's what you see illustrated here, a screen with two slits. What Thomas Young expected to see was simply now two lines on the photosensitive board, and they should line up and be straight because, after all, these particles just travel straight through the slits. But what he saw looked something like this. You can see the bottom of the picture there, the light source coming through the two slits, but when it hits the sensitivity pattern in the back, it looks really weird. And he's going, what happened to the light? Why when it traveled through two slits did it change? And as Thomas Young and others after him, because he didn't know at first, began to think, they said, well, wait a minute, we've seen a pattern like that before. And what we have here is a picture of what waves traveling in water look like if you were to drop an object in two different spots, as you see there on the water. And from one spot, the waves would begin to travel out, and from the other spot, the waves would begin to travel out. And as they meet each other, they start to either build up or cancel each other out. Most of us have seen this happen in water. It happens with sound waves too. It's why sometimes you can be in a certain setting, in a sound auditorium, and if the sound waves bounce the wrong way, you can't hear a thing. It's really odd how that works. So all of a sudden, this didn't make sense. What light was a wave, and then it was a particle? They just weren't sure. Well, a scientist by the name of James Clerk Maxwell came along, and Maxwell, a Scottish scientist working in the 1860s, was studying electricity and magnetism, and eventually is the one who did most of the work in understanding electromagnetism and how that sets up a magnetic field that moves in waves. And he knew that the electricity moved in waves up and down and up and down, and that the magnetism similarly moved. Here it's shown sort of side to side, but both moving in a wave-like way. And from his computations, Maxwell said, wait a minute, I think light moves as a wave also. And he actually put math to what he saw, and being a man of faith, drew up an equation for what must have happened when God said, let there be light. And for those of you mathematicians that can help to understand all of that, God bless you. But James Clerk Maxwell actually demonstrated that the reason light, when it moved through the two slits, developed an interference pattern was it was acting like it was a wave, because that's the kind of patterns that waves do. And the math fit. Now again, all of this is operating very differently from Newton's understanding, and a little bit more confused. We need to move one step further, and we're almost to understanding or gaining our basic understanding that's going to open the way for quantum. We need a fellow by the name of Planck, or Planck, Max Planck, and we're now at the year of 1900. Max Planck, along with several others, was studying a phenomenon known as black body radiation. You can see here on the screen there are some rods that are made out of steel, and of course those are black. The reason they're black, and anything that shows as the color black to us, is because they absorb all the wavelengths of light. Nothing bounces back off. The reason we see color is that depending on the characteristics of an object, when the light hits it, it absorbs everything except certain wavelengths, except certain frequencies. And those bounce back, so that white light is subdivided into red, orange, yellow, blue, green, indigo, and violet frequencies of light, right? There's also ultraviolet, which we can't see. The human eye can't see. So white light bounces all the colors back to your eye, and it looks white. But black doesn't bounce any of the colors. It holds them all together, except when you heat the metal to certain temperatures, and then they begin to glow. And depending on how hot you heat the metal is what color will be shown, and that means a different wavelength of light. So we know, we would see this and go, ooh, that's hot. And we know that that sort of burnt orange to almost yellow color is hot. If you heated it hotter, it might begin to turn blue. And if you heated it really, really hot, and we say that something is white hot, we know that the temperature is even higher. Well, Planck and others were trying to figure out, number one, why this happened. And they also had discovered that these wave frequencies and these colors that were coming off did not match their traditional scientific predictions. They were using the intensity of the light, which is correlated with the heat, and they were trying to use the wavelength of light, because by now they know it. They know what color orange is. They know what wavelength that is. They know what color blue is. All of these things were known. But by applying the heat and applying the light, their theory did not predict accurately the colors of black body metals. On this chart here, you can see this red line running up when they plugged in the numbers from their Newtonian understanding, from their Newtonian classical physics. The numbers just went higher, higher, and higher until eventually they moved completely off the chart, which didn't make sense, because in practice, the black line that you can see is what would actually happen to the wavelengths and the frequencies of the light. So what actually happened and what was demonstrated in real life and in the laboratory did not match at all the numbers and the theory of traditional classical physics. Pretty disturbed by that. And as he was working on the problem, there's a picture of old Max, by the way, kind of a grumpy looking guy. I don't know, I guess if you did math all day, is that what happens to you? I don't know. Anyhow, he was desperate to make the physics of black body radiation work. And since he couldn't figure it out any other way, he decided that he would just fiddle with the numbers and see what would happen. And when he began to do this, he discovered that the results were always off by the same amount. And it was a certain and very precise amount. In other words, if he fiddled with the math and added this exact amount, this precise number into every equation, instead of moving off the chart, it made the numbers work perfectly. Now that number turned out to be sort of strange, 6.6260704 times 10 to the negative 34th power square meter kilograms per second. Now, if you're an engineer or a mathematician, you may know those as joule seconds, and you may recognize this number as now the most famous and important expression in quantum physics. It became known as the Planck Constant. And Planck said, since this happens in every single one of these equations, that's what makes it constant, and since it is always equal to the very same precise amount, he called that amount of energy that was present and needed to make those equations work a quantum of energy. It was a definite quantity, and a number of them would be called quanta. Quantum is the singular form. And that's the expression for a quantum of energy. Okay, as smart as all of these people were, what remained was for someone with a brain the size of Einstein's to put it all together. And so, in 1905, Albert Einstein, who was studying a phenomenon known as the photoelectric effect, Einstein borrowed Planck's idea, and he stretched it just a little bit further to explain one more weird thing that traditional physics could not. Now, here on the diagram, you see a representation of an experiment that scientists of the day were working with, and they couldn't understand exactly why it was working this way, and so Einstein was the one who was thinking about it. Here on the right, you see a depiction of red light wavelengths being inserted into a metallic object. And when that light was shown into, red light is very low, very low frequency. When the red light was shown into the metal, nothing happened. No matter how much red light you put into it, no matter how intense you tried to make it, you could just multiply and make it the brightest, most intense red light you could ever see. Nothing would happen. However, if you turn the frequency up and you put in the middle green light, now the waves are shorter, they're closer together. What they discovered were that these electrons, these particles, began to jump off of the metal. They were emitted, and they came off with a certain amount of energy. If you turn the light up again, and now we move all the way over to the left, and we see the blue wavelength of light, the same thing would happen, only these electrons would come off with even more energy. So low frequency, no energy. A higher frequency, these electrons would be emitted and they would come off with some energy. Higher energy, the electrons would be emitted and they would come off yet with even more energy. All of these were forms of light, but they couldn't figure out what was making the different kinds of light act differently. And so Einstein formulated an equation there, energy equals H, which is the universal symbol for the Planck constant, times the frequency of the light. And if you plug those numbers in, you would discover why there was not enough energy in the red light to make any of the electrons come off. It didn't matter how much light you put in there, that frequency, that wavelength simply could not cause those quanta of energy to be emitted. But the higher the frequency, the greater the energy, and it was always by a factor of the Planck constant. Now, everybody thought that was pretty cool. Of course, Einstein, that's not the only E equals equation Einstein ever wrote. Most of us think that he's much more famous for E equals mc squared. And that's going to come a few years later. And that's a very important development in determining the energy that's in mass. But actually, Einstein won the Nobel Prize for the first equation, E equals hf. At the time, it was a much more important discovery, and it was a puzzle that nobody else could figure out. And I've told you all of that to tell you, what is the payoff for understanding the way light travels and its energy levels and the way it's related to particular quanta of energy? Einstein theorized that light must be considered neither as a stream of particles nor as a wave, but rather as a new form of matter called a wave form. Now stick with me, and we're going to watch this picture that has come up on the right hand of your screen. The waveform behaves sometimes as a particle and sometimes as a wave. And that's why all of those scientists were getting different results in their experiments depending on what they were testing. Sometimes light was acting like a particle when you put it through a single slit and you got this really nice pattern. At other times, light was acting as a wave. And that's what Young discovered when you put it through two slits. And they suddenly began to interact with each other. Those particles then began to act like waves. You can see it depicted here on the picture to your right. This is just a representation of what a waveform looks like. And moving from left to right, you can see that it begins as wave-like, and there's the up, down, up, down, up, down of a wave. And then light moves for a time into a region where it is both wave-like and particle-like, and to the right can emerge sometimes and be seen as a single particle. But in between these moments, it exists as both. And the term wave-particle duality was born. It did not make common sense. It did not make good sense. But the quantum figures, the quantum equations, the quantum experiments all proved to be exactly and precisely just like this. Einstein, working with all of the things that the other scientists had provided as well, basically proved that there was a thing that existed that we'd never realized before, and that for the most part we couldn't see. We could only see how it happened. Now, by the turn of the 20th century and the beginning of quantum understanding, it was possible that a thing could be both one thing and another at the same time. Light can exist as a wave and a particle at the same time. Now, believe it or not, that idea is the absolute basis of quantum thought. And we're going to base everything else we're going to do in the rest of this series on the principle of wave-particle duality. I want to close up pretty quickly with a man by the name of Richard Feynman, who lived later in the 1940s, 50s, 60s, was a working scientist, and probably is the only person that's ever been considered to be anywhere near as intelligent as Einstein was. Feynman was absolutely brilliant and gave lectures on physics that are still taught and referred to this day, even though he lectured in the 1960s. Feynman says this about what I've just showed you, about the wave-particle phenomenon. Things on a very small scale behave like nothing that you have any direct experience about. They do not behave like waves. They do not behave like particles. They do not behave like clouds or billiard balls or weights on a spring or like anything that you have ever seen. Excuse me, I hope I can cut that sneeze out, but if I don't, I apologize. Feynman was talking about the idea that they tried to reproduce quantum behavior in traditional labs, and so they used balls and weights and springs, and they never could get it to work. And he says, look, it doesn't work that way. We are choosing to examine a phenomenon which is impossible, absolutely impossible, to explain in any classical way, and which has in it the heart of quantum mechanics. In reality, it contains the only mystery. We cannot make the mystery go away by explaining how it works. We will just tell you how it works, and in telling you how it works, we will have told you about the basic peculiarities of all quantum mechanics. Feynman is talking about what I just showed you, the double-slit experiment and the wave-particle characteristics of light, how it can be both at the same time. It can also be either or. And that's one of the expressions we're going to use a lot when we think about postmodern society. No longer must something be either or. There is now the possibility that it can be both and, both this thing and that. Again, we are in the postmodern world. Remember, everything is possible. We have the choice between God with us or God, who's He, and religion and science are either cooperating or they are competing. We're looking for the ways that they can cooperate, and we're looking for the insights that we can develop where science and faith actually work together. Well, today it's all begun with light and it is all ending with light. Next time we're going to move a little further into the science, and we're also going to move a little further into the faith. One of our participants in class last week came up with an absolutely stunning realization. He said, oh, now I see why it's possible for Jesus to be both man and God. And you know what? Right up until that moment, I hadn't even thought of that myself. So those are the kinds of things we're going to at least think about as we can. Is going to be titled Untangling Entanglement. And believe you me, it is more weirdness, it's delightful, it's wonderful, and I will see you then.